everyone, I'm back after 2 months hiatus because I'm settling in Canberra. How's everyone? Today, I'm now going to do question 2 of MAT 2022. This equation here is called the Pell equation, and usually Z is set to 1, and the 19 can be any number, like literally any number, except the fact that when it's a perfect square, of course, because if you have a perfect square, then the equation will have absolutely no solutions. So let us focus on part 1 first. Then we have x squared plus ny squared minus 19 2xy squared equals 2, and then substitute z x squared minus 19y squared. And then we will expand both sides to get x to the power of 4 plus 2n x squared y squared plus n squared y4 minus 76 x squared y squared equals to x4 minus 38 x squared y squared plus 361 y to the power of 4. Now, we will compare coefficients for x squared y squared and get 2n minus 76 equals to negative 38. Then, you will have n equals to 19. And then we get the same solution where we have n squared equals to 361. Again, comparing the coefficients. And then we have n equals to plus minus 19. The negative solution will be rejected because it wasn't in the first equation. Now that we have found out that n is 19, find z if x equals to 13 and y is 3. So 13 squared minus 19 times 3 squared equals to 169 minus 171 equals to negative 2. Now, we are going to delve into the world of continued fractions. Every square root can be expressed as a continued fraction. For more, you can just look it up on the internet. But for now, we just say that the continued fraction for square root of 19 can be written like this. 4, 2, 1, 3, 1, 2, 8. Then don't forget the semicolon and the recurring bar. This basically means that you can just truncate the fraction. Like, say you have 4 plus 1 over 2. Then we have 9 over 2. 4 plus 1 over 2 plus 1 over 1 equals to 13 over 3. And then 4 plus 1 over 2 plus 1 over 1 plus 1 over 3 equals to 48 over 11. And then we continue in this fashion. We get 61 over 14 and then 170 over 39. Still not impressed? So we have 9 squared minus 19 times 2 squared equals to 5. And then 13 squared minus 3 squared times 19 equals to negative 2. And then we continue having 48 squared minus 19 times 11 squared equals to 5. Again, and then we have negative 3. And then we have 1. Hey, but wait a second. If we multiply both by 4, then we will have 340 squared minus 19 times 78 squared equals to 4. Why does this work? It's because we are multiplying everything by 4. And then if we take the square, take away the square, take the square root of 4, then we have 2. Basically, this means you can multiply every number before the square by 2 and you'll be safe. Well, that means we just derive our solution. Hence, find a positive pair of whole numbers such that x squared minus 19y squared equals to 1. Again, we have derived it and got 170 squared minus 19 times 39 squared equals to 1. Is this the only pair? No, because just as a continued fraction can provide successively better approximations to the square root, just so that there are infinite numbers of solutions to x squared minus 19y squared equals to 1. That is the Pell equation where the constants usually denoted A is 19. Let's talk about part 4. Prove that there are no whole number solutions to x squared minus 25y squared equals to 1. And since I'm running out of space, I think I better do this. Then, since there are no whole number solutions, do you want to know why? It is because if x squared equals to 25y squared, then that means we can deduce x equals to 5y. Actually, it's the plus minus, but It's still a whole number, and therefore this means that it can never equal to 1. It can only equal 0 or any number as long as it's not 1. Number 5, find the pair of positive whole numbers. And again, the solution to this Pell equation results in the continued fraction of the square root of 17. So you have 4 semicolon 8 recurring. There, much simpler. Then we continue in the same fashion as before. Then we have 33 over 8. Then we have 33 squared minus 17 times 8 squared equals to 1. Are we done with the question? Yes, definitely we are. But no, I'm just going to show you that there are even more solutions to this. So, just like the previous one, we can continue applying the continued fraction. Then we have 260 over 65. And then if we do this 268 squared minus 17 times 69 squared, we get negative 1. How? Well, it's because that the continued fraction is basically a recurring alternating series. Now 4 plus 1 over 8 plus 1 over 8 plus 1 over 8, then we have 2,177 over 528. And we do the numbers, it turns out that 2,177 squared minus 17 times 528 squared equals to 1. Do you know what this means? This means that you can just pick any number which isn't a perfect square, like 8, 17, like we've done before, 19, as we've done before, 964 even, and then you could solve the Pell equation using the continued fraction. And I believe on the internet that there are continued fraction expansions for all the square roots up to the square root of 100, which of course is 10. Now, I don't want to digress too far on this, but since it's a very, very fascinating topic, I encourage you to look it up and if possible, consult your university library for it. And if not, maybe you can just, derive the continued fraction expansions yourself, which myself is something I like to do. But since I had to do this question in such a short time, I had to look it up. But just telling you that this is something that is easily derivable, not like the very, very hard formulas that will take years, probably months to derive. And, well, that's it for the Pell equation question of MAT 2022. See you!